Welcome to the International Solar Alliance Expert Training course. This module is entitled Planning Distribution Network with Photovoltaic Generators and have been developed in partnership with the Clean Energy Solutions Center. My name is Oriol Gomis Belmun and I will be the lecturer for this module. The supporters of this expert training series are the International Solar Alliance, the Clean Energy Solutions Center, and the Carbon Trust. As I said, my name is Oriol Gomis Belmun, and I am a professor in the Electrical Power Department of the Technical University of Catalonia. Together with other colleagues, I work in the research group CITSE UPC, and my work is centered on power systems dominated by power electronics, including renewable energy, both photovoltaics and wind, HVDC transmission systems, and other power converter systems like energy storage or electrical vehicle chargers. This training is part of Module 4 and focuses on the issue of planning of distribution systems with photovoltaics. In this session, we will introduce PV plants as distributed energy sources in the distribution network. For doing that, we will have to introduce the concept of distributed generation and discuss how to integrate it in the distribution network. Later, we will talk about distribution network planning, to later discuss about the impact on line loading and system voltages. Later, we will discuss about the integration with storage and flexible loads, and finally, we will give some examples discussing about the previous concepts. In the scheme, we see a typical electrical power distribution system, which can be used as an example to see the main characteristics of such systems. The distribution system is connected to the transmission system, and it is exchanging a power flow which can be bidirectional. So both active and reactive power can flow from the transmission system to the distribution system or in the other direction. It is usual to have a variable tap transformer in the interconnection between the transformer and the distribution system in order to provide the appropriate voltage regulation. You can notice in the diagram that there are a number of different nodes which refer to different loads which will be connected to this distribution network. Also, there are multiple lines, and you can also see that some dashed dotted lines indicate that these lines can be connected or not, depending on different studies or depending on the operation of the system. You can notice that in the distribution network, we will have both medium and low voltage levels. The grid you are seeing will be based on medium voltage level, but then the different loads connected to it will have additional transformers and it will be distributed in low voltage. Typically, we have a meshed design so that there are alternative paths for the power flows. When there is a failure on one circuit, for example, then we can use another one. And in this case, this should be done using these dotted lines, so connecting them and using those lines for the power flow. And typically, the operation of this network is radial, so there is no loop which is closed in order to avoid multiple possible directions for the power flow. It is important to notice that this is different in the transmission network, where the system is meshed and also it is operated in a meshed way in order to improve the efficiency and the reliability of the system. PV plants are distributed energy sources in the distributed networks. They can be installed in the distribution network as distributed energy sources. This means that we do not have to follow the traditional approach of installing the larger scale power plants and then transmit the power through the transmission network and then the distribution network. In the case of PV power plants, there is also the option of installing them directly in the distribution network. This is a change in the old paradigm of having an unidirectional power flow from generation to distribution. In this case, the generation can be installed in the same distribution network, and for the reason, as it was mentioned in the previous slide, there is a possibility of reversing the power flows and having power coming from the distribution network to the transmission network. Another important characteristic is that distributed generation in general can be based on a small or medium scale units to generate electricity close to the loads. As it has been said, this is changing the traditional paradigm, and it allows also to optimize the use of the network. So in many situations, it will be possible to supply the load with generation which is installed close to the load. Distributed generation project definition and execution times are lower compared to large power plants. The fact that the systems are smaller makes it easier and faster to design, define, and execute the projects, and this is an important advantage. Distributed generation is normally modular and renewable, but not always. We can have examples where it is not modular, it is a single unit of an important amount of power, and also in some cases it is not renewable. An example can be, for example, a gas turbine or a diesel generator which can be installed in the network. The trend in photovoltaics, and we could say also in distributed generation in general, the trend of the cost is reducing clearly more than the costs in transmission and distribution. And for the reason, it is becoming more and more interesting to look at distributed generation, because this cost reduction makes it more interesting for more and more applications. In the figure, we can see the trend in the total cost of PV installations, of solar PV installations. We can see how the levelized cost of energy has been changing from 2010 to 2018, according to information from the International Renewable Energy Agency. We see that the cost reduction is very, very important. It's like reducing the levelized cost of energy in a factor of 3.5, which is a really important change. This has made to have more and more installations and more interest to install solar PV in a distributed way. Distributed generation technologies offer important potential benefits, which will be discussed now, but it is important to see that not always they will provide these benefits. It will depend a lot on the installation and on the proper design of the whole solution. The first point is that distributed generation can provide lower cost of electricity, and it can provide it in two different ways. First one is that the direct cost of energy generation can be lower. We have seen in the previous slide that the cost of solar PV installations is being more and more reduced, and this can make that in some projects it can allow to reduce the cost of the generation directly, because the cost of the energy is much lower than other alternatives. But also it can provide a cost saving which is related to the lower cost associated to reduce transmission and distribution losses. So in some cases we can reduce the losses for distribution or for transmission or for both, and this reduction of losses will imply also a reduction of the costs for the operation of the system, which can be at the end translated to a lower cost of the electricity. It is important to say that this can happen if we are applying good engineering practices in the design of the solutions, but also it can happen the opposite. If we install distributed generation in a location where there are other alternatives, perhaps we can see that the cost of the energy increases, and also that the losses increase, and also the costs associated to the losses increase. So for the reason we are saying that it can provide lower cost of electricity, but it is not always the case. Similar interpretation can be made for the following bullet point, which states that distributed generation can increase reliability and security. So if we are doing a good use of distributed generators, they can increase reliability and security because of their modular nature. We have more generation installed in the system, and after an eventual fault of loss of some circuit in the system, these distributed generators can ensure a proper operation of the system. So it can increase the reliability and security. But if we do a bad installation, this bad installation can provoke that we have worse reliability and security than the system before. The distributed generation can also reduce the environmental impact because we can use more renewables, so the environmental impact of the system can be much better compared to some other alternatives. Also, distributed generation can postpone or eliminate investments in transmission and distribution systems. In some cases, we see that the increase of the demand in some parts of a given region make needed to reinforce the transmission or the distribution network. Some more substations can be needed, some more transmission lines or underground cables can be needed, and a good option is to replace that for other generators or energy storage systems. In this case, for example, if we install PV power plants or distributed generation in some locations of the network, we can avoid to do investment in the network, which can be expensive and difficult to execute. The same can be said for investments in conventional power plants. Distributed generation can allow to postpone or eliminate such investments and replace these kind of investments by doing distributed generation. Distributed generation can also increase power quality and grid support enhancement in the network. This is associated as well to the voltage control. So if we have more generators in the system in a distributed way, we have more nodes where we can control the voltage, where we can control power quality, where we can provide ancillary services. So if all this is implemented in a proper way, we can have a much better integration of the system and we can improve the power quality. Finally, distributed generation can also enhance the system's resiliency, and this is mainly because of the distributed nature of this generation. So we can sometimes, when we have an important problem in the network, like storms, snow, which can lead to multiple failures in multiple lines, in these cases, each distributed generator can create a grid, or different generators together can create a grid and can supply some of the loads, so this can provide a better resiliency to the overall system. Distribution network planning is very important when looking at the evolution of the system, so the distribution companies need to do a proper planning for the future scenarios. Normally, they look at horizons of between 15 and 20 years, and they need to think, they need to decide what kind of investments they are going to do in order to meet the demands they have, both from the load, the expected load, and also respect the power of the quality of the power they are supplying. Normally, the distribution companies are repeating this period every year, so they are doing and updating the planning every year and using the information which is going to be discussed now. The first step is the load forecasting, which determines the load conditions for the corresponding year. The distribution companies have forecasts. They are looking at how the demand is changing, how it is normally it is increasing, but not always. So this allows them to do calculations on the future demand. Later, they are doing a deterministic network analysis. So basically, they conduct steady-state power flows and short-circuit analysis, which are performed to calculate the power flow in the distribution lines, the voltage variations, and also the short-circuit current flows. This is a detailed technical study which allows the distribution system operator to understand what it is the state of the system with the existing power demand and also with future power demands which are being considered. So this can be repeated for the future scenarios they are taking into account with the load forecast they have for each different year, and also looking at different specific seasons of the year where the load can be increased or reduced. If the distribution network does not meet the power system technical and operational constraints, for example, the system power flow does not work and the system is not feasible, the distribution network has to be reinforced. How this reinforcement is going to be provided depends on the different possibilities available. So it can be by building new lines or by using other alternatives like installing power electronics in the system, like installing distributed generation, okay, and or other techniques which can be used. The acceptability criteria of the solution, representing the policies of the distribution system operator and the obligations of to the consumers, are the following ones. First one is the continuity of service. So it needs to be ensured that the service continuity will be kept at all time. Another important point is the maximum allowable peak load voltage drop to the most remote customer. So the voltages in all the nodes of the network need to be analyzed for all the possible conditions in the system, and it has to be ensured that the voltage will be between acceptable ranges in all the conditions. Another important point is also to take into account the maximum allowable peak load. So there is a maximum power which can flow through each of the lines in the system, and in no conditions this has to be exceeded for none of the scenarios which are being taken into account. The reliability of service is another very important factor. So it needs to be ensured that the reliability is ensured in all the scenarios, and also considering different faults in the system. Finally, the power losses need to be kept below a maximum value. It is very important to operate the system in a reliable way, but also to keep the efficiency as high as possible. This will require also to optimize the voltages in the system and the power flows. So in order to meet all these requirements and looking at some possible reinforcements which can be needed, it can be needed to consider additional system elements. Of course, the first option and the conventional option, it could be to reinforce the lines, so to build new overhead lines or cables to have more capacity in the distribution network. But in addition to that, we have some other options which can be used. First one is the distributed storage devices. So we can install energy storage in different strategic locations of the network, and in this way we can provide some of the services which have been discussed before. Another possibility is to use flexible loads, which can be connected or disconnected, or also sometimes they can be adjusted to a different power level depending on their needs in the system. These flexible loads can be very useful and can provide a service very similar to the one provided by energy storage systems. One specific type of flexible loads are electrical vehicles chargers. We can optimize when we are going to charge the vehicles, and optimizing that we can achieve a better integration of the solar PV and also a better system of functioning. Power system flexibility is clearly a very important characteristic. As we have discussed, this can be provided in many different ways. According to EPRI, power system flexibility is the ability to adapt to dynamic and changing conditions. For example, balancing supply and demand by the hour or minute, or deploying new generation and transmission resources over a period of years. In modern power systems, flexibility is becoming more and more important because we have the non-dispatchable renewable systems, and in order to ensure a proper system operation, flexibility from other sources is becoming increasingly important. Optimized system planning, as we were discussing before, can be achieved considering additional units providing flexibility. Multiple different optimization methodologies can be used to optimize the planning. The optimization methodology is chosen depending on the constraints and objective functions defined. The use of PV generation can reduce line overloads in many cases, but not always. It depends on the system power flows. Studies are needed to identify the relevant cases, including also the worst cases, in order to understand how PV plants can impact the system operation. The main quantity impacting the grid is the difference between load and generation. So the ideal case is when the PV generation equals the load. So basically we can say that distributed photovoltaic systems can be used to reduce distribution loading, but also we need to take into account different cases, and while it can be achieved, this reduction of loading not always will be achieved. So we need to study this carefully in order to ensure that we are doing it properly. Here we will see an example of this. In the figure, we see an example of the load in a distribution line connecting a large hotel without any kind of PV generation. We see that for different hours of one entire day, the active power is varying in a range between 250 and almost 600 kilowatt. If we install some PV in this same hotel, we can see what happens with the total power. Okay, in the left figure, we see what happens when we are connecting PV for a peak power of 300 kilowatt. And in the right side, we see what happens where we are connecting 750 kilowatt of PV generation. In the left side, we are seeing that when the PV is starting to generate power, the line loading is being reduced, and the minimum loading in the line happens more or less at the same time when the maximum PV production is achieved. If we keep increasing more and more the size of the PV power plant, we see that something different is happening. In the figure in the right, we see that when the PV starts to generate power, then the loading of the line is being reduced. Before 10 o'clock, like at 9 approximately, this power arrives to 0. When it is 0, it means that there is a balance in the system. So all the load of the hotel is supplied by the PV plant. But when the solar radiation keeps increasing in the next hours, what it happens is that the power flow is reversed. What we are seeing in the figure is the absolute value of the active power. So what happens from 9 to perhaps 6 or 7 afternoon, what it is happening is that the power flow has been reversed and the power is coming from the hotel to the distribution network. The hotel is behaving as a generator because the power generated by the PV power plant is larger than the demand of the hotel. So there is a maximum after noon which arrived to 400 kilowatt, which is an injection of power from the hotel to the network. If we keep studying this example and we look at the highest loading in the line which is connecting the hotel to the network, we see that when we have initially 0 solar power, we had an initial value of loading measured in kilovolt amp per phase, which is lower than 300 kVA. When we increase the solar photovoltaic penetration, then this grid load power is being reduced, and it arrives to a minimum when we install about 300 kilowatt. Between 300 and 900 kilowatt, the highest loading is maintained constant. But if we install much PV than that, what it happens is that we start to increase the loading in the system. What it is happening is that in this case, the highest loading depends not on the loading of the system, which was what it was happening before. From this point on, the highest loading depends on the generation. So the PV generation is so big that it provokes the maximum loading in the system. If we keep increasing more and more the solar power, we will see that we are increasing more and more the loading of the system. What it is basically happening in this case is that we are loading the system so much because we are installing a very large PV power plant. So in this case, we are not anymore achieving a reduction of the loading of the system. Instead, we are increasing the loading of the system because of the PV plant. If in the previous example we analyze how the losses of the system are behaving, we see something similar. For low levels of integration of PV, increasing the PV means losses reduction. We are seeing it in the beginning of in the left side of the figure. Increasing the PV means that we are reducing the power flows because we are supplying directly power from the generation to the hotel. So we are reducing the currents in the distribution network, and therefore we are reducing the losses. There is a point where we are optimizing, and if we keep increasing more and more the generation, then we see that we are increasing the losses. This happens for all the applications. At the end, the ideal case is when we can achieve a good balancing between the load and the generation. But if we are installing too much generation, then what we see is that the effect is not positive anymore, but it is negative. In this figure also, we see not only how the losses change, but also we see how they change for different power factors. At the end, it is not only important to control to have a given power injection from the photovoltaics. Also, depending on the reactive power we are exchanging between the photovoltaic plant and the system, we can achieve different losses. We discussed in other modules, that the solar inverters can control also the reactive power they are exchanging with the grid. Depending on the value of the reactive power, we can basically control the voltage at the point of connection of the solar inverter, and having the appropriate voltage and reactive power can allow also to optimize the losses. So for each condition, we can see what it is the optimal condition of the solar inverter and adjust the reactive power in order to enhance the losses in the network. Another very important quantity related to the integration of solar photovoltaics in the distribution network is the voltage. We know that the voltage is a local measurement, so it depends in the different nodes of the system. In each node of the system, we can have a different voltage. We know that solar PV impacts the system voltages. Active and reactive power flows change with the presence of PV generation. So, since the power flow changes, then the voltages in the system will change as well. It needs to be coordinated with the distribution network equipment for voltage control. So we can use different equipment, and this equipment needs to be coordinated with the solar inverters we are using. This equipment can be capacitor banks, standard capacitor banks to control reactive power, transformers, also to adjust the voltage and reactive power in the system, and in general elements with reactive power control capability. In the right side of the slide, we see a figure showing the distance to the substation and the voltage. We can imagine that the different points in the figure shows different nodes which are more and more far away from the substation. When we are close to the substation, the voltage in all the cases is the nominal voltage, or the voltage which is imposed at the substation transformer. But then we can see some evolutions depending on the solutions we are considering. We see that if we have no capacitors and no PV generation, we have the behavior following the blue line. So the voltage is dropping quite fast. If we want to keep the voltage higher, one option is to use capacitors, which is what we have with the black line. In this case, the voltage will be reduced, but it will be reduced more slowly. Also, depending of course on the capacitors, the behavior could change. This is only an example. Another example is when we have the capacitors, and additionally we have generation in the line, in this case PV generation, we see that the voltage can even increase. Okay, this increase can be provoked by the capacitors or by the PV generation. Normally the generation will have a higher impact because basically the generation is injecting active power. In the distribution network, active power is normally more important than reactive power for voltage control. This is different in the transmission network, where reactive power is more important because of the inductive behavior of the lines. Here we see an example of a real project, which has been reported in the reference paper, which is mentioned below. In this case, we see a connection to the network and different feeders connecting a number of different strings of panels. We see that we have 4 different feeders and different measurement points where we are going to show the results later. We see that we have many installations here of different powers, always in the range of tens of kilowatt peak. About the measurement points, we can see that the measurement point 1 is very far away from the transformer. It is at the end of the feeder 2. The measurement point 2 is at the end of the other feeder, and measurement points 3 and 4 are closer to the transformer. If we look at the power we have in the total system, we see that most of the time the power of the PV is smaller than the power in the loads. So normally we are in the consumption zone, but during some parts of the day, when the radiation is maximum, then we see that we are injecting actually power to the network because the power generated by the PV is larger than the load. If we look at the voltages and some of these points, we see that at the transformer secondary side, we have this distribution of probability. We see it is quite narrow, which means that normally the voltages are quite stable, and they are normally around 236 volts. This is the phase 2 neutral voltage of the system. Okay, we see that we have some variations, perhaps between 233 and 239, but most of the time the voltage is quite good. We see the same for all the different phases 1, 2, and 3. If we look at the end of the line, at the measurement point 1, we see that the variation of voltages is much higher, and we can have lower voltages, perhaps arriving to 231, and then also increasing up to 245. We see that the behavior is slightly different for different phases. So we see that the higher voltages are happening for the line 3 especially, and also a bit for the line 2, where the line 1 is a bit more stable and tends to have lower voltages. This is probably related to the different connection of phases, both in the load and in the generation. If we are connecting more solar PV generators to some of the phases, these phases will tend to have higher voltage than the other ones. In the slide here, we see multiple different points of different measurements of different phases, and also we are seeing the maximum tolerance level which can be allowed, okay, which is 244 volts according to the standard used in the study. And we are seeing how the voltage in all the phases is changing, also depending on the injection of power from photovoltaics. We see logically that the higher the injection of photovoltaic is, the higher the voltage is. This is expected because we are injecting power, and this will increase the voltage of the nodes where we are injecting the power. Here we see another example where we are considering the use of energy storage combined with distributed photovoltaics. Energy storage can be useful to reduce overloads in the distribution network by providing support to the voltage control in the distribution system. Additionally, the inverter can help with reactive power support. So the impact will not only be in terms of active power, but also in terms of reactive power. The inverter of an energy storage system is very similar to the inverter of a solar PV system. Okay, and also we have this controllability both on active and reactive power. All this can be analyzed as an optimization problem addressing multiple objectives. Basically, the two key objectives here are the peak shaving, which could be also discussed as the reduction of the loading, and the other one is the voltage control. Also, we will see that optimizing peak shaving normally will not be the same as optimizing the voltage control, for the reason we have multiple objectives which need to be addressed. The optimization can help to select the technology, locate and size the energy storage system and the inverter. Okay, these optimization techniques can be very useful for this purpose, and they can be used to select energy storage systems and also to select and to discuss about the installation of solar photovoltaics, depending on the flexibility we have in the system. For example, in the study we are including here, which is a study from Tan and other authors from the KU Leuven in Belgium, it is discussing about a case where the solar PV installation is already defined, and they are discussing about the possible installation of battery storage in different nodes of the network. We are seeing here that we have a 250 kVA transformer, which reduces the voltage from the medium voltage to the low voltage level, from 10 kilovolt to 400 volts. And then we have a complex system containing, which is a radial system containing different lines. In each lines, we have different kind of connections. Some of them are normal houses, which are loads, and others are houses which include as well some distributed generation, some solar photovoltaics. The study is discussing where we should install energy storage in order to have a good integration of the system, in order to reduce the peak shaving, and also to have an acceptable voltage level in the overall network. The studies conducted in the paper have shown very interesting results. The Pareto fronts in the figures show the trade-off between peak shaving, which is related to the maximum grid apparent power, and voltage regulation, which quantifies the voltage deviation of the nodes. This allows us to see the optimal location of the energy storage system, and also it allows us to compare between having nothing, having only an inverter, and having an inverter with an additional battery. In the figure in the left, we see the Pareto front, and we see how the voltage regulation objective, which is the variation of the voltages in general in the network, how this voltage regulation is behaving compared to the peak shaving objective. We see that when we have better peak shaving, then we have worse voltage regulation, and the other way around. The different lines in the system show the installation of an energy storage system with a constant cost and constant technology. So in this figure here, we are not discussing about the cost and the technology, and we can compare where we are when we do not have any storage system, which is this point here, okay? And then also we can see how the node we select influences the results. So if we are installing the energy storage in node 2, we get this Pareto front characteristic. But if we install it in node 4, we have much better voltage regulation, and also we have quite good peak shaving. This means that the node 4 is much better than node 2. And remember that we are always talking about fixed cost and technology. So we are not investing more. We are only discussing where we are installing this energy storage system. But we see that if we go to the nodes 17, 61, 67, 71, 42, then the result is much better. We are obtaining much better voltage regulation objectives. This is mainly because we are going to the nodes where we have worse voltages. So if we are installing the energy storage in these nodes, we can improve quite a lot the overall system behavior. In the figure in the right side, we see another case. In this case, we are comparing doing nothing, which is the same point as before, and using an inverter or using a battery. we see that using only an inverter with reactive power control capability increases a lot the voltage regulation, and also it helps a bit with the peak shaving. If in addition we install a lithium battery, then we can reduce much more the peak shaving, because then we can use the active power for that purpose. So basically, from the study we see that the candidate nodes for ubicating the energy storage systems are the nodes 17, 61, 67, 71, 42, which are the extremes of the different lines in the network, while the nodes 2 and 4, as we saw in the previous slide, are not as good as the other ones. They are closer to the transformer, so the impact they can have in terms of voltage regulation, it is much smaller, which can be considered quite obvious looking at the system, but for more complex systems, this kind of a study can be very applicable. In this study, only one energy storage installation is considered, but also we could think about the option of installing many different energy storage systems in many different locations. And also in this distributed approach, it would be interesting to see if we can improve the results. If we consider different technologies for the batteries, and also we see at what happens when we are increasing the investment, where we are increasing the cost, we see another interesting Pareto front, which shows the trade-off between the peak shaving and voltage regulation, but in this case for different costs per year. We see that in this figure, the location is constant. We are not discussing about the best location now. We are only seeing what happens where we are increasing our investment. And we see logically that the more money we invest, the better we move along the Pareto front. And we are seeing that for lithium batteries and lead acid batteries as well. Another example is related to the flexible demand, in this case in the form of electrical vehicles. We see in the scheme here that we are considering a system, and this is a result from a study from the TU Delft by Chandramouli and other authors. And in this case, we are considering PV panels installation, 10 kilowatt peak. Then we are considering here a DC-DC converter and a DC link, where we are connecting electrical vehicles to charge electrical vehicles in different manners, and then we have the grid connection. Here we are seeing different charging strategies which can be considered. So in gray, in the figure in the top left, we can see how the solar PV power injection is changing in different hours of the day. So we see logically that in summertime, the power injection is much higher compared to winter. But also we see that we can take different strategies for the charging of the electrical vehicles. So each of these colored lines is showing a different strategy. Basically, the study is addressing and comparing the different charging strategies in order to find out which is the best strategy which can be used in order to have a proper integration of the solar PV and the electrical vehicle charging. We see in the table here the energy exchange with the grid for a week. And we see that depending on the electrical vehicle charging profile, the power fed to the grid and drawn from the grid can be substantially different. So we can order the different strategies and see which one produces a more reduced exchange with the grid. This means that basically we are using directly the solar PV to charge the vehicles, and then we have a more reduced use of the network, which is at the end what we were trying to achieve. If in addition we consider the utilization of energy storage, then we can do much better, which is what we are showing in this other diagram, that where we are increasing the capacity of load storage, and it allows us to reduce the annual energy feed or drawn from the grid. So basically, if we combine the electrical vehicle charging with an optimization of the storage, then we can obtain a much better result. Finally, as a summary of this module, we can say the following. In the first place, PV power plants can be installed in the distribution network as distributed energy sources. They are not the only distributed energy sources we can have, but probably it is one of the most interesting ones we can have nowadays because of the modularity they have and for the very competitive cost they have. Solar PV plants can contribute to reduce or increase the loading of the lines. We have seen some examples where they contribute to reduce it, other examples when they contribute to increase it. Okay, so good engineering practices have to be applied in order to ensure that we reduce the loading of the lines. Also, PV plants have an impact on the overall system voltages, which needs to be studied. In many cases, we can use properly PV plants so that we improve the voltage profiles in the network. And this is what we are going to try to do in most of the cases. Flexibility is very important, and energy storage system or flexible loads can be integrated with PV systems and need to be integrated to have a more and more flexible system. We have introduced in the module some examples to show practical cases. In the first example, we have shown how distributed PV can reduce or also increase, if not well sized, the loading in the distribution network. In the second example, we have shown how PV can contribute to control the voltage in the distribution network. In the third example, we have shown how using energy storage combined with distributed PV can provide improved results both on voltage regulation and peak shaving. And we have seen some Pareto fronts in order to see the trade-off between the two objectives, voltage regulation and peak shaving. Finally, in example 4, we have shown how PV can be hybridized with electrical vehicle as an example of a flexible demand solution. And thank you for your attention. This is the end of this module.